All right. Well, welcome everyone to this very special edition of the webinar that we're about to host. And just want to thank everyone for taking time to be with us. I am joined here by Sean Varley from Ampere. Sean, welcome.
Hey, Mark. Nice to be here.
Yeah, absolutely. It's great to have you. And Ben Lee from Supermicro. Ben, welcome.
Hi, everybody. Nice to be here.
Yeah, I know both of you have some awesome material prepared. And I'm Mark Donegan from NETINT. I'm going to kick things off and let's just dive right in. Now, let me say this. If you have any questions, make sure you add them in the chat. We're going to do our very best at the end to get to those. We already have, I think, 12 or 15 that have come in from those that have registered and already sent their questions in. So we really want this to be interactive. I can't promise we're going to be able to touch on everything, but we'll certainly do our best during the webinar. And obviously, you can reach out to each of the panelists and the respective companies afterwards. So we're here for you. But let's jump in to the presentation. All right. So we are going to talk today about really a whole new way to architect servers for video streaming and video encoding applications. And I think it's important, to just start with what the problem is. We're all engineers, and sometimes it's fun to go look for an engineering solution. But at the end of the day, the best engineering solutions are those that solve problems. And so the problem that we're really setting out to address today, that I'm assuming that some of you or even many of you are feeling or facing, is that you need more processing power, or muscle. And this is because there is limited space in data centers. So you might literally be running out of rack space. And as we know, in certain countries around the world, certain regions, there's just a limitation. You can't build more data centers. There are no more racks available. So what do? So you need more muscle. Obviously, costs are just absolutely skyrocketing. And cost, especially in power, we saw across the EU in particular over the last 12 to 18 months, I've heard numbers as high as a 4x, even a 5x increase in some regions. And that obviously is not sustainable. So if we can do more with less, then that certainly is going to help us on the cost side. And all of this comes back to really just our consumers, our customers, our subscribers, our audiences are clamoring for more video. And whether it's more content that our systems need to ingest and process, whether it's more users we need to deliver content to, we need more output capacity. So that's kind of the problem statement. And that's where we're going to start here as we look at what the solution is. And really the way that we're going to address this is to reinvent the server for video. And there's three ways or three core focuses that we're going to look at in this webinar. And the first is how to engineer it, how to make the server for video encoding, video processing, video streaming smaller and faster. You can make them smaller, you can make them faster. Rarely can you do both. And that's what's super unique about what our three companies are here to show today is that you can actually reinvent the streaming server to be smaller and faster. We are also going to show you how we can make it cost 80% less to operate. And that seems like a really, really big claim. It is a big claim, but it's true. And we're going to show you the data behind that. And at the same time, we're going to show you how this new configuration, this new architecture, can actually increase throughput by 20x. Again, very bold claim, but it's true. So let's actually look at the numbers here. So we're all three of our companies, we're engineering companies. So we like to start from an engineering basis. And the data really speaks for itself because the engine behind this new architecture is an ASIC. And if you're familiar with ASICs, you might already know that Google built their own ASIC for YouTube. The reason why they did that is because they were able to eliminate 10 million CPU cores. Now, what's super interesting is they didn't actually eliminate CPUs from the workflow. Instead, they were able to then repurpose. So for codecs that they don't support in their silicon, they can encode, they can decode. There's obviously other operations that they use across the YouTube service that they can then deploy on software running on commodity CPU. And so today, what you're going to be seeing is the incredible power of a VPU, so a video processing unit that is dedicated to very high quality, very high density, very high velocity video encoding, video transcoding. And when you make that with an ARM CPU, Ampere is going to talk in greater detail about their solutions. But when you bring those two together in a single chassis, it's a real powerhouse. And so just to set the stage here about what a VPU can do for you in video, the data here, if we start on the left, what we're looking at is the environmental impact. And if you were to do the same workload, so let's say 10,000 live channels, and you might say, well, we only have 10 channels. We only have 100 channels. We have 1,000 channels. Don't worry about whether you have 10,000 or you don't. The percentages remain the same. So 10,000 live channels, the environmental impact of encoding those live channels on ASICs would be basically 1% of all the carbon emissions that would be emitted would be 1% would come from ASICs. If you were to say, well, what if I just use GPU? What if I did it all on GPU architecture? And name your brand, name your model. Our testing shows that the results are not that much different, whether you have a favorite model from NVIDIA or from AMD or from someone else. 16% of the carbon emissions emitted would come from GPU operations. So you could say that's 16 times, if we kind of look at it that way, what would come out of an ASIC. Now, where it gets really scary is if you're using public cloud, even if you're using private data center, if you're doing it in software, so open source, x264, x265, SVT-AV1, maybe a commercial software solution, 83% of carbon emissions, of the carbon footprint, is coming from CPUs. And I think we've all heard that all of the public clouds have made very public announcements. We've heard about the net zero in 2030 initiatives. And so this is a focus. Everybody's looking at this. Everybody's trying to play their part to get to net zero and ultimately reduce carbon emissions. But the fact is that as long as we keep our video encoding function in software running on, there's only so much that you can optimize and reduce. So that's on the is your OpEx. And so if we look at the OpEx here, for 10,000 live channels, you actually amazingly can operate on ASICs 10,000 live channels, and it's about $131,000 a year. If you move that to GPU, you can see how the cost increases. And if you go to CPU, it's just crazy expensive. It's nearly $6 million. Very, very significant swing. And then the number of machines that's required. And you can really get a sense when you look at the graph on the right, 1,250 servers to run software, software encoding operations. And so you can see where that environmental impact is. Those machines are hungry. They require a lot of power. Power, of course, just directly the output, the exhaust, of that power is CO2. It's carbon emissions. So the data really speaks for itself. If you're not considering ASICs, if you're not considering that topology, then your costs are going to be significantly higher, and your environmental impact will be probably much more than you would like it to be or you need it to be. So what's the answer? What's the solution? Well, we're introducing, and what we're really talking about today is our Quadra video server. And this is the particular version that uses the Ampere CPU, the Ampere ARM SoC. And this is just super powerful because the combination of NETINT VPUs with the Ampere CPUs gives us that smaller and faster footprint, costs 80% less to operate, and increases throughput by 20x. So as a quick data point, this 1RU box here can actually encode more than 300 1080p streams. And that's live, and that's with broadcast quality. And by the way, that can be AV1, that can be HEVC, that can be H.264. And so unlike software, where because H.264 is a less complex codec, you can get higher throughput with H.264. You're going to get, about 3 to 4x lower throughput with HEVC. And then when you go to AV1, it's even another 2 to 3x lower throughput than HEVC. So it always scales down. With ASICs, it scales perfectly linear. It's perfectly flat. So the performance curve, the density curve is it's the best. All right, so let's talk in a little bit more detail about what's smaller and faster, what the components are that enable this. So what you'll see here is you see the server. And by the way, this is a representative server which we do sell. It's available commercially. But as you're going to see from Supermicro, they have a number of chassis that are all fully certified for Ampere. They're certified for NETINT. So if you're looking at this, or if you're familiar with the Supermicro line and you're thinking, that's great, Mark, but we need a different server, not a problem. This is just representative, but it does happen to work in a lot of video streaming context. So what we have here is 10 of our T1U VPUs, and again, VPU is video processing unit. Each one of those can do 32 1080p 30 streams, and we're going to show you some really interesting data with deinterlacing and some other functions that you can run on the CPU. But right now, we're just talking about transcode performance, so you can just get an idea of the raw encoding, transcoding performance. And the power inside the VPU is our Codensity G5 ASIC. This is purpose-built. This is designed by us, by NETINT. It has a very extensive IP block, and I'll show you in the next slide a bit more about what actually comes inside this chip, but it's very, very capable. And then the very unique thing is that with a powerful host CPU, because the heavy duty encoding transcoding is happening on the VPU, functions like deinterlacing, functions like software decoding. So you want to run David. Maybe you need to do MPEG-2 decoding. Maybe there's some other format that we don't support in the silicon that actually can run on the software. And we're going to show you some performance results that are quite amazing, because the host CPU actually is practically idling even while the VPUs are fully loaded. So that is a really amazing advantage of this particular architecture. But there's another function that maybe some of you have attended this webinar because you saw this and said, we need to learn how to do that. So obviously, generative AI and ChatGPT is hot, and it's finding its way into a lot of video workflows, a lot of production workflows. Whisper is a model by OpenAI that actually enables highly accurate, real-time automatic transcription. So imagine if all of your video streams were transcribed and subtitled in real time. So even while I was talking, and clearly Vimeo is not running Whisper, or we just haven't turned that function on if they are. But it could be a situation where you're broadcasting a live stream, the speaker's talking, and in real time, the subtitles are showing up, just as if you had the world's fastest typist there. And that can run on the server, all in a single box, and just give you astounding flexibility. So let's look real quick. I'm going to go over this. If you want to really do a deep dive into the functional blocks, just go to our website, go to netint.com. A ton of information is up there, data sheets, there's white papers, a lot of information. But for those who may not be familiar exactly with what's included in our Quadra line, which is the VPU, our second generation ASIC, here's a functional block. And you'll notice on the left side there's the video processor, the video engines. On the right is the audio engine. In the middle, we have an AI block. So we actually run 8 of the major frameworks. There's up to 18 TOPS of power. So that's TOPS is obviously trillion operations per second. And there's a lot of unique models that can be run. There's some incredible functionality that can be run in that red block there. We also have the 2D engine. The 2D engine is for cropping and scaling. So if you need to create a transcode, you can do all that right on the chip. So you could bring in a high resolution, high bit rate stream, maybe 4K P60, and then you can create a transcode of multiple ladders all inside the silicon. Very, very efficient. But the video processor supports AV1 encode, VP9 decode, supports H.264 decode and encode, HEVC decode and encode, JPEG, so image decode and encode, and then obviously YUV for both decode and encode. And then on the audio side, you can see the formats that are supported there. All right. So now, the second hallmark of this solution is that it has to cost less to operate. This comes right off our website, so I would encourage you to if you want to dig into this a bit more. I know the fonts may be a bit small depending on the device that you're looking on, so you can go to our homepage, in fact, and you can see this diagram here. But what we've modeled is just another scenario where we looked at a certain number of streams, and we compared it based on going on AWS. A lot of our customers are moving off AWS, and the most performant instance for video encoding is the Graviton 2 instance. And so we, chose to give AWS the best advantage possible. And we modeled running on Graviton 2 instances. That's the first scenario. The second scenario in the middle is if you co-located servers and you put those in a co-location, you ran the software yourself. There's actually some advantages to doing that. If you find some good pricing in a colo, we were able to model, a pretty significant savings. I mean, it's more than $100,000. It's nearly $120,000 savings by just moving off public cloud and going into an on-premise or a colo type location. But where the savings really stacks up is when you move to ASICs, and it's largely because you're able to cut your machine count down by a factor of 10 or more. Even by a factor of 20. So you don't have to buy as much hardware. You're not spending as much on power. You don't have to spend as much on rack space, all of those costs. And it's just a tremendous advantage. So it's a really massive advantage there. All right, and then the third, benchmark or pillar, if you will, for this solution is the increased throughput. And I'm going to show you a couple. We have a whole lot of data. Again, go on the website. You can look, especially in our blog, just a ton of data in there. So if you love data, we have it for you. But what I wanted to pull out here is specific what you can do when you really fully utilize the CPU, the super powerful ARM CPU that Sean is going to tell you about next, and what you can do with this for deinterlacing, for example. So we know that there's still many services that have to deal with maybe 50% or more of their incoming video being interlaced. And if you're going to stream that out to, well, any device, it needs to be converted to progressive. So you say, well, how do I do that? What's the most efficient way to do that? And we've got some just really amazing results here. And so if we look at the individual throughput, let's look at those at that data first. And there's a couple scenarios. So if you were to take 1080i in and then transcode that to 1080p. So we're doing the software on the CPU, we're doing the deinterlacing, and then we're using the VPU to encode. And this could be, this could be literally any of the supported codecs out. So, you could be bringing 1080i H.264 in, and you could be converting that to HEVC. You could be converting it to AV1. You could be converting it to H.264. Doesn't matter. You can get 95 streams out from that single one RU box. So that single box, you could get 95. So you bring 95 live streams in, 1080i, deinterlace it, transcode it, and all of this is happening in real time. So this is all a real-time operation. This is not VOD. This is not offline. This isn't file processing. This is live. If you have 720p, so in Latin America, for example, there's still a fair amount of 720p services, and there's many services that want to move from maybe satellite, where the initial distribution is satellite, and it's interlaced, maybe even still MPEG-2 over a little bit older network, and they say we want to go to more modern streaming boxes. We want to be able to deliver to a TV, for example, connected TV. Then a perfect application is this solution where you can get 195 channels. So 720i in, and then what goes out for delivery to your connected devices, set-top boxes, media players, browsers, whatever, is 720p 30. And then if we look at at 576, then you can see there you can get up to 365 channels, which is just really astounding. Now, the graph below, the combined throughput, what this represents is on the same machine, you could have 1080i to 1080p 30. You could have 10 streams running. You could have 720. You could have 100, and then 576, 100. So think of this as like, maybe there's a situation where there's legacy devices in the field that don't support 1080p, or maybe there's just mobile devices, and they say there's no need to send 1080p to it, but we want from that same server to create those different resolutions. So again, on that same server, the exact same hardware, you could get that combined throughput performance. So super astounding and really an incredible use case. Now let's expand this testing a bit more. So one of the things that is very common in video is that there are new codec generations that are always coming, and also there's legacy formats. So maybe you need to decode, or you need to deal with some sort of an incoming file or incoming source that isn't supported on our silicon. Well, the beautiful thing is that now there's a very well-developed ecosystem of software players. So we looked at two codecs here. We looked at AV1 and MPEG-2. Obviously, MPEG-2 legacy, but sort of like interlaced, it won't die. It's still very prevalent, and in many systems, MPEG-2 files need to be decoded. So for AV1, just starting there, we use the very popular open source David, which, by the way, if you're wondering how to play back AV1 on devices that still don't have hardware support, David is a wonderful, very efficient, really highly developed open source player. Highly recommend looking into it. But in this solution, we were actually able to decode in software 96 1080 streams, so 1080p streams. So we were able to decode 96 channels. And again, the beautiful part about this is, remember, the VPU capacity is largely unaffected. So even though in this scenario it did utilize nearly 100% of the CPU, you still have the full capacity of the VPU because it's silicon, and the overhead just to communicate on the NVMe bus is minimal. It's virtually zero, so it's very low. So that is a really wonderful advantage. Now, moving over to MPEG-2, the density increases significantly, and it's just a function of the encoder and of the codec. But there we were able to get 320 streams, and only 30% of the CPU was utilized. So you can see in a scenario where you might say, I need to decode MPEG-2, I need to do some deinterlacing, and maybe I want to run a whisper model so that I get this automatic subtitling that's happening in real time. You can see how it's not crazy to think that you can run all of that on a single box and still get pretty amazing density, density that certainly you can never get in software. All right, so I'm going to wrap up my section and turn this over to Sean at Ampere. But really, the punchline is ARM ARM CPU plus NetInt VPU just unlocks a whole new world of value. And Sean Varley, take it away. Tell us about Ampere.
Thank you, Mark. I appreciate it. Maybe I'll start here with just an introduction to Ampere as a company. If many of you are not familiar with this company, we're about 6 years old at this point. We are a fabless semiconductor company that is building server processors. We have a history of basically being able to build not just one processor, but a lot of processors. We're turning them out at about a 12 to 14 month cadence. And the processors that you will see as we get into Ben's section, here being utilized here are Ultra Max processors. So the Ultra and Ultra Max family of processors are the first cloud native processors. Ampere coined this term. Our mission really is to turn out processing that is for a sustainable cloud, whether that cloud is in hyperscale data centers, edge data centers, regional data centers, or actually out on the far edge. All of those servers or server class devices consume a lot of power in today's world. And that's one of the things that we started out our lifetime really looking to change and build out a sustainable cloud. So let's see. I cannot seem to advance the. Oh yes, I can. Sorry. All right. So the just to kind of give you guys an introduction into what the value proposition really is here. A cloud native processor such as the Ultra line is essentially built to have a potential of around a 4x shift in efficiency. And when you look at efficiency, we're terming that from a point of view of performance for power or energy consumed. So it's performance per watt in server parlance. And that is a potential 4x shift using cloud native processors like the Ultra line. And that is kind of built out. If you look at performance in this chart, is essentially the performance is measured by spec int rate, which is a common micro benchmark for measuring server performance. And then we're looking at the power consumed, and you can see here it looks like the lines got a little shifted when we converted to PDF, but essentially the Ultra processor is running at about half the power, but with twice the performance. And that is the basis of this potential 4x shift in efficiency. Really kind of groundbreaking technology for server processing in terms of efficiency. And again, that's what we're going for. That's where the sustainable cloud comes from. This efficiency is predicated on several different factors. If you look at a legacy x86 processor, you're going to see things like turbo frequency or hyper-threading. Also, you might see scale-up accelerators, things that are put into the processor for specific accelerations that may be, attempting to do what Mark just talked us through for the first part of this entire webinar, which was utilizing a purpose-built ASIC or other accelerator for doing very specific jobs like video encoding or video transcoding. And so this is things that you might find in a legacy x86 processor, but you're not going to find those things in an Ampere processor. Ampere is about building general purpose processors that are power optimized with consistent performance, meaning we run them at consistent frequencies. We do not do turbo frequency. We do not do hyperthreading. We are actually building the most efficient single-threaded cores, and we're packing a lot of those cores into one processor because we're a scale-out company. This gives us the ability to add processing capacity in increments all the way up to the full capacity of the actual socket. This gives you linear scaling, and there's no variance, almost no variance, no noisy neighbor, no congestion that actually gets in the way of fully utilizing a core to its capacity. This gives very predictable performance and allows for a very, very high performance at a low power. That is essentially the value proposition of an Ampere processor. Now, to illustrate this, I'm going to walk you through a quick example. This is a web service example. Why do I use this example? It's an example that is very familiar to all of us. Everybody that ever has used an app on their phone or browsed on their PC has used a web service, and it's easily translatable for most people to understand the power and the versatility of this cloud native architecture. So I ask a fundamental question. If you took a 1.3 million requests per second load as measured by the HTTP requests coming in, since we're in video here, we're talking about YouTube or any other type of social media app that is actually drawing video off the internet. And this allows us to actually create a load that we ask the fundamental question, how many servers or racks are required to service that 1.3 million requests per second? The answer, if you do this math based on performance metrics that we have taken on real world applications in a 4-tier web service. What do I mean by a 4-tier web service? A 4-tier web service would have a front end, a caching layer for objects and a caching layer for key value, and also a back-end database. In this case, we used Nginx for the front end, which is a very common front end. We used Redis for the key value store. We used memcached for the object store, and we used MySQL for the backend database. So those are 4 of the most popular containers used in the world today. That's the basis of the analysis that you're seeing here. So the power and the answer to the question of how many servers are required to service that 1.3 million requests per second is essentially 36 CPUs or 36 1U one-socket servers, which you just saw Mark present. Those servers running 128 cores in this particular analysis are what's required to service that 1.3 million requests per second. But if you contrast that to the x86 ecosystem, you're going to see 54 CPUs or maybe 27 servers for AMD. You're going to see 82 CPUs or maybe 41 dual socket servers for Intel. That's nearly 2.5 to 3x better performance per rack. And if you translate that into power, getting to what Mark was talking about earlier, how do you reduce the OpEx of these infrastructures? Now you start to see the real advantage to using a cloud native processor. We're going to consume about 12.7 kilowatts to actually service this load. You compare and contrast that with 22.7 or nearly 35 for Intel in kilowatts to service that same load with that number of servers, and you're seeing the disruption, the actual value of running a cloud native processor at scale. This was chosen, the 1.3 million request was chosen because the 12.7 kilowatts actually fits into a modern rack. for the most part. Racks come with a rack power budget. That power budget ranges from about 10 to 14 kilowatts on average. Of course, you can find ones that are higher, you can find ones that are lower, but for this example, we used about a 13 or 14 kilowatt rack. And this is disruptive because then you can start to see the additional benefits that come from this. We can fit those 36 1U servers into one rack in both power and in space. But now you start to see where the power efficiency adds up in aggregation. Takes 2 racks for AMD, takes 3 racks for Intel. That is super powerful because now you're saving space. And recall, Mark talked about this earlier. Many geographies in the world today are now both power and space constrained, and they're looking for ways to make major changes without having to go to exotic cooling or have to build more data centers, which they can't even get permits to do. So 1/3 to space, 1/3 to power, and essentially about 2.5 to 3 times the performance is the value of using a cloud native processor to do many of these bulk workloads, of which video is one of those. So we'll look a little bit more at this and talk about kind of our value in video services. I talked about Nginx earlier. The video services example, or the web services example that I just went through was using Nginx as the front end. And you can see here the fundamental efficiency factor being about 4x, 3.8x better than the furthest away x86 competitor in power efficiency, or performance per watt. And that is a fundamental foundation of this type of technology. Talked about the predictability, and unfortunately, this chart got munged in the conversion. But what you would see here, if it was correctly rendered, what is that the distribution of latency in a Ampere server is very tight and very high in terms of a histogram. Whereas in x86, you'll see a much broader shouldered distribution of latency as measured by requests per second or request response time in an Nginx scenario. So what you're seeing is a very predictable architecture. This is fundamentally necessary in video services because, of course, latency is one of the big bugaboos of video delivery. Any amount of variability in latency and responses through video is going to show up as jitter. It's going to show up as delay and lag and all of those sorts of things that annoy us all on a day-to-day basis. The other one that we've talked about a little bit is linear scalability. As you add more and more to the processor, you're going to see a linear profile in terms of its capability to process additional video streams or what have you. And so that allows data center planners and service planners to much more reliably manage the capacity of their infrastructure because they can count on the server to deliver incrementally more performance in a linear fashion. Many people would understand that an x86 server, there's kind of a rule of thumb out there in the industry around essentially provisioning at about 50 or 60% capacity of the server in terms of utilization. That's because of this roll-off that you see in linear scalability. An x86 server with hyper-threading will roll off in every instance, and so that nonlinear behavior has actually established sort of a rule of thumb or a behavior in the industry of not provisioning your servers higher than about 50% utilization. And that's just a rule of thumb that we are shattering with the cloud native processor. And we have designed these processors to actually run at 90 to 100% utilization. That means you're running all of our cores. That's why we put them in the processor. Okay, so the final thing I'll talk about here is power efficiency. And you're seeing here that in an Ampere server, we are running somewhere between 40 and 50% below the power at the socket level of an x86 server. And that is an example of the raw kind of power efficiency of the processor, bringing the amount of energy required to run a service down. Now, let's talk a little bit about deinterlacing that Mark talked about earlier. A couple things to note in the ARM ecosystem, because these are ARM-based cores. We do utilize a number of the improvements that are put out there into the open source industry. In this case, we're looking at FFmpeg. And FFmpeg now has excellent support for the AArch64 architecture, or the ARM architecture. And this kind of shows just in the more recent versions of FFmpeg from 5.0 all the way up to 5.1 and 6.0, the improvement in deinterlacing performance across those versions has come up significantly. You can see this up to 3x better on 6.0 versus the earlier 5.0 FFmpeg versions. This is not uncommon in the ARM industry. So this is one of the reasons why we wanted to throw this slide in here. You need to look at GitHub. You need to look at some of the commit comments and also go to the Ampere website. We have a lot of information about what kind of versions to get when you're looking at utilizing the ARM infrastructure for these types of workloads, because the more recent the OS, the more recent the libraries. Mark mentioned David earlier. You know, these kinds of things, you want it to run the more recent versions to get the highest performance out of the ARM architecture. So running automatic speech recognition, or Whisper, as Mark had talked about, is a fundamental value here. Utilizing the spare cycles. When you look at using the code density ASICs that Mark talked about, this is an offload of some of what could have been run on the CPU. That's an actual huge benefit, because now you have all the capacity of those server cores to do other things like Whisper or some other computer vision model in AI parlance. These are the kinds of things that you can do with that added capacity now that you've taken it off the processor by utilizing the code density ASICs to do a lot of the transcoding. So if you were to do that, looking at the transcription model data, I'm showing you Ultra Max, which is the Ampere processor in raw inferences per second. And I'm showing you this on PyTorch. So these are open source frameworks utilizing the Whisper model, showing it against Ampere Intel Generation 4 and Intel Generation 3, and also the AMD Generation 4 and Generation 3 processors. Ultra Max, which is a Gen 4 DDR4 platform, outperforming all of those other competitive CPU platforms, but also outperforming both the NVIDIA T4 and the NVIDIA A10. So these are amazing results utilizing an Ampere multi-core 128-core processor to do things like transcription. Now, the last thing I think I'll say here is that this is an example of utilizing a domain-specific architecture. This entire Quadra video processing server is an excellent example of how to get the best efficiency out of a purpose-built platform for a specific use case, like video processing. Utilizing a VPU like the code density ASICs and the Quadra products that NETINT builds, along with a low power, high efficiency performance or processor like Ampere's Ultra and Ultra Max. In this case, we're looking at like a 96 core processor running it somewhere south of 200 watts. And this is going to kind of deliver the best in class processing, the most sustainable, the most efficient processing available to the market today. So I think here I'm going to now pass it off to Ben for taking us kind of home on this entire webinar. And Mark, I see you coming back on here. We're going to talk a little bit about combining this all now into the Supermicro chassis. Is that right?
That's right. Yeah. Thank you, Sean. That's awesome. Super exciting what you guys have designed. So Ben, why don't you take us home, so to speak, and Our VPU and Ampere CPU has to live in a chassis. And so tell us about how Supermicro hosts this amazing solution.
Sure. Thank you, Mark, and thank you, Sean. Okay. Yeah. So big thanks to Mark and Sean for setting stage. And I think just my turn to share the Supermicro's perspective along with this journey, right? And first, I really want to talk about the collaboration. As you can see, we are teaming up with MPA and NETINT, and it's really a powerful collaboration. And the goal is to lead the way in the video streaming by developing such outstanding solutions. And I have to say, I've been very fortunate to witness the collaboration between our engineers, right? So the way we have come together, sharing the knowledge and skills, that I think it's a great testimony to our commitment to setting a new standard and introduce innovative solution to the video processing. So here, I really want to talk about this future ready flexibility about our server. So this is our server, and our server utilizes the Supermicro building block principle, and just to ensure the flexibility and the readiness for the future technology challenges. So we call a module design that's showcase our agilities to adapt and integrate emerging technologies. This enables us to respond to the rapid and technology evolution, and so we also can really encourage the innovations. So such agilities, I think, is very critical to this kind of fast-paced technology environments, right? So this is really keep the solution really be the forefront and be the leading edge in the industrial. So one thing really highlights very important is such approach, not just provide a future-ready flexibilities, but also help to mitigate the risk and also assure the product qualities. And this is very important also for this kind of video streaming server. And so we have very solid testing and validations to assure the solution will be not just efficient, but also be a very robust video processing technologies. Okay, and then I really want to talk about this kind of end-to-end support. So I think at Supermicro, our commitment is begin way before the product deliveries. So we will engage with customers in this kind of detailed architectural discussions, and we will bring the right experts, such as Ampere or from the NETINT, and so we can deep dive into this kind of architectural nuances. So to ensure every solution is optimized and for the customer environments, right? And then at the proof of concept stage, we provide a very robust technical support, right? We will always be the first line to provide the support, and we will address the challenge and fine tune the performance. And I would say this is very important to meet the expectations and for performance, but also for some reliability criteria. So, and then our dedicated support will extend to the post deployments and offer like end-to-end technical support and after service is care, such as RMA, advanced replacement, things like that. Right. So this is really a commitment. Like we want to ensure that continuous and a smooth operations to our customers, and just reinforcing a dependable experience well beyond the purchase. So again, our goal really make sure everything running smoothly for our client and ensure reliability every step of the way. And then I think this section, I just want to try to echo what Mark and Sean just mentioned. We have, with this building block principle, we have a broad product family. And so this is just a high level look about Supermicro, we call them mega PC product families, right? So this lineup, just like it's really again to our building block principle, and offer variety of the solutions, like cloud gaming, like high performance database servers, and deep learning and AIs. So each product is based on the Ampere CPU and with our like chassis, right? And then we all design for optimize the performance, and so we can help customer to address different kind of workloads, right? So and we can tailor make to the different solutions with the broad spectrums of the computing needed. So a video streaming server is just one of the big area we're focusing, but some area like cloud gaming, AI is also something will be very interesting, and we love to offer such solution to customers. So yeah, so to wrap up, right? So I would say let's spotlight this amazing video server. I think it's a great example to our collaborations. It combines the Ampere powerful CPU and with the NETINT advanced encoding technologies. So, always in our Supermicro, robotics and the chassis and also the motherboard. And that's to achieve the impressive 320, channels, at the 1080p P30 resolutions. And it's also very power efficient. We just really consume 500 watts, right? So again, I would say our collaboration not just set the standard, but also refining the efficiency in the video processing. As we always advocate ourselves to be a green partner in ID solutions. So that's really make a great example for us, right? So we are very excited to see the impact, and hopefully that will be part of your projects, or in this industry we can contribute more. I just have this kind of quick kind of introduction, and hopefully we can spark some ideas and some excitements to you. So back to you, Mark.
Okay, awesome. Well, thanks, Ben. Sean, wonderful presentation. So we're moving into a Q&A session here, and as I said, if you have any specific questions, anything that came to mind as you were listening, just type them in the chat, and we'll do our best to get to them. But really excited because I know it's one thing to hear vendors talk about their solutions, and it's another thing to hear about the same solution from a real user, a real customer. And so I'm joined here from one of our partners who is right in the middle of deploying this exact architecture. And Alex, I guess I would like you to introduce yourself, and first of all, and tell us what you're doing, what you've deployed, and let's hear about how this is benefiting you.
Yeah, sure. Thanks a lot for having me. So GNL is a managed service provider located in Germany with branch offices in San Francisco. We design, build, and manage multi-vendor solutions for audio and video processing and delivery. We work both in the cloud and on-prem, both with on-prem systems that we operate ourselves and that our customers deploy in their own premises. So we need two kinds of machines. One is for streaming servers. So we have Ampere Supermicro machines as streaming servers, but we also needed machines that could do heavy load transcoding with a low power consumption. So we were looking for something that is flexible, that is using not a lot of power. So we came up with the combination of NETINT cards, the Quadra cards that you have mentioned before. We wanted to run it on Ampere ARM processors to even lower the load that we have and get linear performance also things that Sean mentions. And we needed a host system that is affordable and flexible enough to carry all that. So we integrated that before you announced this machine as a single setup. And we just installed the last 10 cards of your Quadra cards last week and set up everything here. So yeah, we are running it with using the SDK by Ideas in the UK, the Norsk SDK, which allows us to do very flexible things with that. And we're currently load testing everything for setups that are similar to what our customers currently are doing with third-party encoders like Elemental Live machines that they're currently using. So we use the same setup in terms of the rungs that we have. So usually these customers have 5 bit rates per channel, usually only AVC. We are also having 3 HEVC rungs on top of that, so 8 streams in total per channel. And currently we get 8 of these rungs per card on it. So it's a huge amount of cards, a huge amount of streams and channels that we can support there. Very amazing.
Amazing. Yeah, that's awesome. So what about, support for SMPTE 2110 and SDI, and there's some other interfaces and technologies. Are you working with any of those technologies?
Yes, exactly. I would have imagined that most of the setups that we do have 2110 already, but most of the customers who were interested in this setup here still have SDI on-prem. So we started with SDI. So the systems we built have 16 to 32 ports that we support with SDI ingest. We are working on 21 next, and we will include DVB-S input as well.
Awesome. Yeah, well, it's perfect, Alex, because some of the questions that came in, somebody asked about support for SMPTE 2110s. So there you go. Yes, fully supported on this solution. And SDI, there's many deployments with SDI in the field, various configurations. So yeah, that's amazing. Well, I think we'll come back to probably have some other questions for you, but thank you for joining, and thank you for sharing. So I guess Sean, we have opened up some really interesting opportunities together in some markets that are very price sensitive, and wondering if you can comment from kind of the CPU perspective of where you're seeing maybe some new use cases even get unlocked. I don't want to put words in your mouth, but I'm thinking cloud gaming and AI inferencing and things like that. But yeah, tell us where ARM is slotting in and really filling a need that the other architectures just can't get there from a cost basis or energy or some other vector.
Absolutely. Well, thank you for that kind of lead in, Mark. And happy to kind of share some of the things that we are seeing. ARM, a relative newcomer to the server market, but it's been around obviously for ages and is the most widely deployed architecture in the world. If you talk about everything, that are in all of our handsets, right? So this is an interesting kind of time in the compute industry in general. What we're seeing is the adoption of the low power architecture and the extremely predictable, entire solution that we've put together from an Ampere perspective to get dense computing into any form factor, from a hyperscale data center, which you see examples of this adoption everywhere from our customers, Google, Microsoft, Oracle, a lot of the worldwide cloud suppliers, also customers of ours, to the Graviton architecture that's in AWS, right? So there's a lot of entry into that big container, largest container in the world, and then you can kind of go all the way down the spectrum. Regional data centers, regional CSPs, managed service providers that are doing, bringing processing closer and closer to the edge. Right, because that's kind of sort of what we see is happening, and we also have customers all the way out of the far edge in devices, in autonomous vehicles, in satellites, in a lot of different sort of applications where the container now isn't the hyperscale data center. It is a very small box, something like what we just saw with Ben's, one U server, all the way down into things that are even tighter than that, with
Mm-hmm.
no ability to do any sort of active cooling. And so
Mm-hmm.
bringing the power down in all of these kinds of applications is really, really fundamentally enabling, right?
Mm-hmm.
And that's kind of what we're seeing across the board. But to maybe a few of the use cases that you mentioned, yes, cloud gaming is definitely kind of coming on again, pulling that sort of content into a user's handset at the edge, where
Right.
of course the latencies have now gotten down to a point where it's a doable thing to stream a game across
Yeah.
a much more closer in terms of proximity with fewer hops kind of connection. So we see that, happening in general.
Yeah.
Content and processing, AI processing, getting out closer to the edge.
Yeah, that's right. Yeah, it's awesome. Well, Ben, you touched on a pretty wide range of chassis and form factors and configurations. I know that we focused right now on the one, in today's webinar on the 1RU.
Mm-hmm.
Is there anything that maybe you'd like to share with the audience about what Supermicro is looking at, either in the future, or you've announced, that might be interesting in terms of new form factors and the way you're thinking
Yeah,
about?
sure. So as I said, we call it building blocks approach. So we can have this kind of combination from different kind of the form factors, right?
Mm-hmm.
And again, first I want to reiterate that the cooperation between MP and the NETINT has been really great, right? So just what I mentioned, we will start with some architectural discussion with the customers, and then when we will just provide our device and bring the right people to have some discussion. Like what Sean just mentioned, the cloud gaming is important to incorporate the GPU, but the GPU
Mm-hmm.
has different kind of the options, right? So we can start with this kind of architectural design discussions to select the right GPU. And then from Supermicro's perspective, it's so important that we show our expertise from the system engineer perspective, right?
Mm-hmm.
So we have to do the validation. It is kind of small, like BMC, things like that. Then we'll assure like every pieces were put together, perfectly, and
Mm-hmm.
hit the performance that we expected. And then we will discuss about how to optimize the cost through like a different configuration, the memory, the hard drive, CPU.
Mm-hmm.
It's really these kind of small nuances, but that's make a big difference. So that's something we
Yeah.
will different highlight. And one thing I'll highlight is that we have partnership with Sean and his team and the Ampere, continue to chase the technology evolution. Right, there's a new CPU coming next year, and we already have some like early sample that ready for for the test. So I'm very
Yeah.
happy with what you guys always So yeah,
Amazing. It is an amazing partnership, and I think,
yeah,
I referenced it earlier in my piece, but just to make sure in my section, just to make sure it comes out, and so nobody thinks that there's only one solution and it's only the 1RU and it's only
no,
that.
no.
That is, there was a question, so I'm answering a question here, but also just giving broader perspective. There's a question about how we sell the solution,
Uh-huh.
and so in terms of NetInt, we obviously sell the VPUs. So if you already have chassis that you want to deploy in, we have PCIe form factors as well as U.2. Again, go on the website. You can check out all the options there. We also do, because some people would just prefer to get the complete box, and they want to kind of get the whole server loaded. So we do sell it. that way. And of course, if there's some very custom configurations required, then all the parties involved here are very happy to have that discussion. There was another question that came in about pricing. And so again, configuration dependent, but I think the best way to think about it is, we have put the benchmark out there of 300 live streams in a single box. And so that translates to roughly about $70 a stream. Now, hopefully that's an incredible eye opener, because a lot of us are familiar with maybe software licensing, where maybe it's $70 per stream, but that's an annual software license fee, and then you still have to operate the CPU. This is one-time investment. So, when we talk about the economics of the solution that we've covered here today, it's truly breathtaking, and quite remarkable. Alex, I think I can recall some of our first meetings, and and maybe I'm stretching, but I think you had your eyebrows raised, when you first came across some of the claims, because they're so amazing. It's
Definitely.
common for people to believe it can't be true, but it is. So
absolutely, and it is surprising to our customers all the time if we show this. This is really amazing. And to answer one more question that we see, if there is some kind of a control plane management system, so that's one of the parts that we add on top of the system. So we integrate with all the single sign-on solutions of the customer, so that they can use their Active Directory to have their staff use all the systems, and then have a web interface where they can operate all the stuff, and that scales well with the amount of channels that you're talking about here. And still adding capabilities to add video overlays and add logos and confectionize the content that we are processing with your cards, with the CPUs, and with the Supermicro servers.
Yeah, thank you for covering that, because it is true that we're talking today mostly about the hardware, and obviously there's the application layer, there's a software around it that really makes it all come to life and delivers the solution. And I know that GNL does a great job there. So, and like you say, leveraging Norsk, and there's other solutions too. So, well, we've gone a few minutes over, and so I think we better wrap it here. But thank you to the presenters, and thank you very much, Alex, for joining us. It was wonderful. And again, if anybody wants to reach out, feel free to reach out to Supermicro. You can reach out to Ampere, reach out to NETINT. We're happy to make connections if you're not sure how to get to to the person you want to talk to. But thank you again. Really appreciate your time and joining us today.
Thank you, everybody.